The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
We are the Hawaiian Volcano Education and Resilience Institute, HVERI for short. A lot of people know us from the 2018 eruption of Kilauea in the Lower East Rift Zone. Working under Hawaii Tracker on the Facebook group. Since then, we've been trying to carry on and take the lessons, the hard lessons that were learned during that eruption and try and prepare for the next major disaster that comes to our island.
Yeah, and so we do that through two different programs. One is volcano education, and the other part is digital resilience, which we address through online groups on social media. So the way the two programs work together is that the social media networks end up being a distribution pathway for all the information. And having that network in place means we can provide more than just volcano education, but any other preparedness information as well.
What we were working for really came about in the Mauna Loa eruption in 2022. Within hours of that eruption starting, we had the mayor, Mitch Roth, we had USGS HVO Ken Hahn on the stream trying to help flush out a little bit of the ongoing because it's so new. It's completely different from our previous major eruption, which was 2018.
One of the things that Talmadge and I were talking about was how do we deal with social media? It was something we needed to figure out and get right. Our job is to get information to the public and make sure that the public get it as well as possible and as correctly as possible. When Philip and Dan started coming to and live streaming the meetings, it was great because we were reaching more people than we normally would. So when the eruption actually happened, we had this relationship. The interviews we did during the eruption, the most fun ones were the ones with Philip and Dave because they were more relaxed, and we knew we were getting to the local community, and people were asking questions. So those were the best. I think I just want to really give a shout out to those guys and how we worked as a team on this eruption. It really worked out well, and we got to a lot of people we wouldn't have normally gotten.
Aloha everyone. Aloha everyone, I'm geologist Philip Ong, here with Mr. Dane DuPont from a nonprofit HVERI, the Hawaiian Volcano Education and Resilience Institute. Today is Thursday, January 16th, 2025. Kīlauea has begun its fourth episode of its most recent eruption at the summit. So we got plenty to talk about today. as well as we have a special program that starts in about 1 hour from the USGS in the Volcano Awareness Month that we'll bring to you guys, hopefully live as well at 6 p.m. Hawaiian time. So that was a whole lot of just intro right there, Dane. How are you doing today?
Oh, doing pretty good. Been pretty busy. Volcano's always keeping us on our toes with now with episode 4.
All right. Yeah, for sure. So let's see if we get the right thing on the screen here. So we've had a little bit of a hiccup starting up today. It's been a little rougher than usual, but I thought I could play in the background here a little bit of what's been happening today in the summit while we discuss what's going on here, right? So that's really the story. It's been lava's back at the summit, and so lots to see. We won't cover all of it, of course. We're just going to basically, with our limited time today, just look at what's happened today and leading up to it over the last week. And we'll have to leave some of the stuff we normally would do until next week for the sake of time here. So yeah, anything else before we get into it, Dane?
No, if anybody got any questions about this eruption, we'll be doing that in the first half, and then second half is going to be the Volcano Awareness Month presentation. So load them up in the beginning, and then we'll do a Q&A before we kick it over.
Perfect. All right, so let's get our screen rearranged here and get ready for our summary for the week. All right. Aloha, everyone. This is our Hawaiian volcano summary for January 16th, 2025. Kilauea has resumed its eruption at its summit in Halema'uma'u crater inside of Pele, the main caldera. You see here a time lapse of the KW camera as this eruption restarted from the vents in the southwest, and over the last 30 or so hours has produced this pad of lava that's clustering in the southwest part of the crater. And as the other episodes have done, is progressing further to the east across the crater floor as we speak here. So a lot to see up in a national park, and visitation is heavy, but great views from everywhere on the east and south sides of the caldera here. So that's the main story, is that the eruption has restarted. We have some views of the eruption released by the USGS. This is just from today, looking down into the crater here. So you see the south vent and the north vent, both high fountaining. Some of these fountains have exceeded 300 feet high in the last 24 hours. But there have also been some collapses of the vents, especially this south vent, which once the collapse occurs, blocks off some of the fountain and reduces the height of its eruption there. So a lot ongoing to see visually on a volcano. The USGS put out an alert last week following the occurrence of glow on those same vents and the continuation of inflation and ground tilt on a volcano that had exceeded the threshold needed to restart episode 2 and episode 3. And so due to this, USGS put out this possible restart window. And towards the tail end of that window, the lava fountains cooperated and returned here in the southwest. So this map from yesterday is showing just that small area of lava in the southwest thus far, as well as showing the elevation gain, which is very little. In fact, it's more spreading thin across a larger area than the early eruptions in the sequence, going back to 2020. There were some precursory deflation, inflation events that corresponded to some lava outputs on the crater floor, some subsidence and oozing of lava that indicated some disturbance there, or possibly just overturning of a deep pool, before the lava flows come and flood the area where you can now see the current gain in depth of lava on the crater floor there, just since yesterday. That now is at about 5 meters or so, between 15 and 20 feet. The ground tilt has now begun to deflate at Kilauea summit, reflecting the release in pressure as this episode continues to track, while the East Rift Zone is also deflating in response as well. Earthquakes have gone down. They did climb up a little bit before this most recent episode began, but since then have been decreasing. And in locations, they've been clustered mostly around the summit as well as the south flank, with very little action on either of the rift zones of Kilauea there. So we expect earthquakes to stay low as eruption continues producing lava. And that's really the story in Kilauea, is how long will the episode last? Having seen that the first 2 episodes lasted about 15 hours each. The third episode lasted over 8 days. And so here we are on the second day of our episode 4, just guessing how long this might last, perhaps days as opposed to hours now. And that's the story in Kilauea. Mauna Loa continues to be quite quiet. Here are earthquakes over the last month at the Volcano Summit in a typical background fashion. Earthquake rates are still quite low following the eruption in 2022. These are the last 5 years of earthquakes, showing earthquakes per month. And you can see how low we are in Mauna Loa. However, the volcano does continue to still rise. Here is a plot of GPS at the summit showing elevation rise. And you can see that the volcano is very steadily just inching its way upwards over time as magma continues to fill it and swell it up more passively. And that's our Hawaiian volcano summary for this week. All right, so let's switch to our hazard summary next, because what happens at the beginning of these eruptive phases and episodes is that a lot of gas is coming out at the beginning and producing these high fountains, and that gas can actually produce the biggest threat to people if lava itself is not going to be impacting communities, which is the case now. All the lava is within a national park, within the crater. It can't really escape out of there. So it's really a perfect lava stadium, as we've called it in the past, where you can really be anywhere up and around a rim and looking down into it and seeing spectacular views right now, right? With no threat of lava coming toward you or towards any people at all, in fact. But the gas is an issue. So we turn, as usual, to the VMAP, VOG Measurement and Prediction Project out of University of Hawaii at Manoa. And they combine the weather forecast with the gas emissions, which are currently input as 10,000 tons per day out of Kilauea from right here. And that results in this distribution pattern of the VOG, the volcanic fog produced as a result of the interaction of the gases in the atmosphere. Right, so that means it can produce not just the raw gas, but also little particles of sulfates and little things that are really, it can be irritants to your respiratory system. And on top of that, the lava itself can cool in small strands of glass we call Pele's hair, or tiny little droplets. And those things can also be carried by the wind and become hazards for breathing as well. Right? So some of the reports today show that there's Pele's hair wafting around the whole volcano area, in fact. So you can see here that normally we have trade winds from the northeast that blow a lot of this fog towards the south. And so in some parts of this animation, that's what you see. But other parts you see it, Kona winds, what blows north towards Hilo. So you're really getting a large effect across much of the island here today. And what often happens after this is much of this fog will wrap around the Kona side and be trapped on the onshore, offshore wind conditions there. So we can expect fog impacts on the island for several days at the very least here, and beginning with the Hilo and volcano areas and likely wrapping around over time. We can look at our Purple Air Citizen Science Monitoring Network. This is just people having monitors on their houses and see what we see now. And you can see there is some high values around volcano and north as well at Kulani. Not so many right now in the southwest, but you are seeing higher numbers picking up here in the Kona side already, and in fact throughout the saddle and North Hawaii as well. So very interesting to see how this can actually affect a wider area. And if we zoom out to our windy SO2 layer, you can see here that this cloud is quite large offshore as well from Hawaii. So it's certainly a drop in a bucket globally, but here in our vicinity of our state, you can see it's the most major thing going on. So that's our hazard summary on the gas. We'll do a little bit more because we could have the eruption in a national park. We could come back to the national park monitors. Let's see, we're getting a current date here today, so that's good. We're getting weak wind conditions. Northeast at 2 miles an hour is not very much at all. So they're showing the circle of the area of impact, meaning a VOG could possibly sit in this area. And this includes many of the overlooks. So certainly pay attention to national park guidance if you are visiting any area, and especially if you have respiratory sensitivities. right? Because there could be some below average air there when the winds are weak like this. And as an example, let's just go to the visitor center itself here. And we can look at, for example, particulate matter, PM 2.5 at the National Park Visitor Center. And this here is the threshold for a national ambient air quality standard right there. So you see that they've come up and down, mostly in the green. It did get into the yellow yesterday when this eruption actually began. And so certainly could be the case where it wafts back over here. And if we look at SO2, you see a similar pattern as well. This is more the pure gas, and this would be the VOG products with the particles in it as well up here. So both of them an issue there, right? And you can see the wind direction, how it's been spiking, flipping around in that area as well. And that's the concern for the VOG spreading to further areas from the national park. So that's the gas hazard. That's the really the biggest thing to worry about. And other than that, everyone should go out and try to enjoy the amazing views. And that's what we'll focus on here next, is the observations, the visual observations that we crave for so long between eruptions, and now they come fast and furious. Things are changing incredibly fast. So there are several releases. We'll start off back at the end of last week when we actually had Katie Mulliken from USGS on the program. And she mentioned they were taking this overflight the following day on Friday to look into the vent to try to answer the question that we all had: why was the vent still glowing? Was it just a chimney being hot, or was there lava near the surface? And so they flew, took a lot of aerial photographs of this area, right? But I'll focus on these two. Right, there is one, and what you're seeing here is looking down. This is the crater wall, almost vertical in there with the debris slopes at its base. And here's our south vent, kind of shrouded behind this fume, and here's our north vent, right? And if we zoom in, you can see that in the north vent, right there in that puka, that little hole, that little opening, you can see the surface of lava, not that far underground, right there. Right? There's a lot of other features through here. This is the big cone that's around it. This reddish streak is a collapse of that cone, and a lot of times the lava becomes this reddish color because it's actually baking and oxidizing in this presence of this gas, right? And our lava has a lot of iron, so it basically gets that baked, rusty color right in there. So that's just the cone collapsing. But if you look closely, as the USGS did, you can see there's other areas like right in here. That is actually a little glow of a lava flow. Let's see if I can get it any bigger even, right? Getting a little pixely, but there is a glow of a little flow of lava, maybe something like this, right? It seems to be coming out of this vent. This was visible already on Friday. And when we consider the pattern that we've seen in the past of how these vents have reactivated after putting out sluggish lava flows and then having fountaining begin, this led them to put out their first status report suggesting that the window for the fountains to resume was upon us. And we'll get to that here more in a minute. But here's another view of that north vent, looking straight down into it. And it's about as big as I can get that little pad of lava to look in there. But you can see clearly there's lava right there. It wasn't just a glowing rock, and especially when you combine that flow outside the vent from the other source in the south, pretty convincing that it was essentially right there. So that was one set of images, and then after the eruption actually began at 9:15 in the morning on Wednesday the 15th, yesterday, there are some other images such as this panorama. See, this is a place where the public cannot reach. This is the closed road on that northwest side of the caldera, the west side of the caldera. And so you see the view of the two vents on the crater wall and the flow starting to spread to the east there. And one really interesting thing here, you see how the lava coming out has a lot of this dark texture here that looks a lot like an a'a flow, these a'a flow textures. And that's something that you often do get if you have less gas in your magma, for example, right? The flow is more sluggish and more likely to break into blocks than flow as a big sheet where the gas is more evenly mixed into it, for example. The smoother silvery stuff that we call pahoehoe. So interesting to see that kind of sluggish lava getting flushed out of there as events are building up. And this is something we've seen a little bit before. You see there's a couple other these spots of black of these earlier flows of these other stages as well, whether it was lava getting flushed out, or we've also had, as a lot of ponds in this whole area over here in the southwest, once it spills over and starts flooding the other side of the crater, you can also have some lava that's already been degassed, essentially producing some of these flows on the crater floor there. That's something that's interesting and fairly new. We haven't really seen flows in the crater floor in any of the other recent summit eruptions that I can recall at present right now. Yeah, we have had rubble and bits of islands of the cinder cone, as we can see tons of these all through here as well, but never quite an flow to my memory, and so that's something we can dig into more in the future here. So, right, that's just one image there, and see some different perspectives here. And this is essentially the same kind of captures as we had in that initial video that I had to share for you guys there. So you see during the time they've parked the USGS vehicle, the tephra is still falling and it's landing on the hood and against the wiper here. And so they collect this and do chemical analyses on this. And the first analyses are coming out, although we don't have the information between different episodes quite yet. Here's how it looks. Big chunks of new lava spatter on the ground, mixing with the old stuff that's been crushed underfoot for a while. There's about the size of it, the size of a glove, some of these big chunks there and there. And all in the meantime, they're out setting up all their measurements and their high-speed cameras and doing all kinds of documentation and science on top of reporting to us what the conditions are around events. There's a lot of other data being collected that's not quite as important to put out live, but it's important to collect it live. And so, yeah, the USGS has put out this new map yesterday showing the extent of the flows in that southwest part. Many of the other stats didn't really change a whole lot, but we do have this new map that has a cross-section that now adds up the 2023 eruptions and the current eruption here at the very top, right, showing our current depth of fill. We're up to this depth of fill, 1,378 feet or 420 meters, right, which is still below where we were before the 2018 collapse, this is the shape of the crater back then. So while we have filled all of this inner crater more quickly at the beginning because we had more of this flare shape, right? So the first eruption filled the whole bottom part of the cone, then the next one a big chunk, and each one afterwards has been thinner and thinner layer. And now that we've overcome this edge of the down drop block right here, the collapse a little less than that inner crater, we have a lot larger area across to pave our lava flow. And so our resulting eruptions are likely to continue like this, to be quite wide, but fairly thin in the grand scheme of things. So that's a nice updated view. And then we have this video, which I wish it was easier to play with sound for you guys, but I'll just skip it for now. And you can find this on the USGS site with sound, but sound is would be these chunks of rock hitting the pavement as if you had just dropped a bunch of marbles on the floor, for example. Just clink, 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 something like that, right? Might be almost like what you might hear during a hailstorm when you have chunks of ice hitting the ground and hitting around you, except you see it in clear skies here. Let's see the USGS working there in the background. The fountains themselves, they roar, like they're producing this roaring sound that you could hear from miles away. Today I was at the volcano house, and from there, quite clearly, when you don't hear people talking around you, you can see that you can hear that roar of the fountain from really far away as well. So that's captured in this video, but also this dynamic nature of the lava being flung in the air, falling back down. You can see the fountain heights seem to vary. Sometimes it's taller, sometimes it's shorter, different kinds of pulsing. I imagine myself that there's different sizes of gas bubbles in there. You have huge bubbles and smaller bubbles, and they kind of come at different frequencies. And so sometimes you have big changes in the burst, and sometimes you have lots of little ones in it. And in the meantime, it all keeps shooting out and splashing down. It lands on the walls, tries to accumulate and build the cone, but most of it's flowing back down into the crater through those channels. Very quickly, within a few yards of the vent itself, it's forming that silvery skin, that crust, which at night you see the glow through it, and you see like kind of cracks in the crust, spiderweb fracture structure on there. In the daytime, you see more of this silver pattern right there, right? So really fascinating images here, video from the USGS. About as current as you can get with a view from where they can show us. So there's a lot more media online, which you can find on Hawaii Tracker. But I thought today we just focus on USGS video since we are a little bit short of time and their stuff is also accessible. All right, so that's a little bit of a longer compilation video from USGS on the fountains this morning and the fallout of Tephra. And you can imagine the Pele there that comes along with that. If there's big chunks like that, you can see chunks falling from the camera even here, but you can see chunks like that, and you can imagine the smaller stuff is wafting even further and further away. All right, so yeah, there's the USGS video. And we do have a few more images to share. This is another release put out here from the fountains today as well. This is the one I was showing you at the beginning. Let me pull that one back up. And it's looking at similar features, a lot of spray and a crater wall there. It appears that the fountain's now in the south. This vent over here a little smaller, and this is something that they said was a result of the collapse of the vent in that area. And let this come back to the beginning here. That's more of that panorama view. There you see some of the dark flows surrounding this lava pad that's forming. Like a pond, lava shooting up through this ponded lava right there. So what we saw in the video, it was actually a hole with a glow within it. And now you see there's a standing fluid and the fountain is shooting up through that. And it seems like there's a ponds in this upper level, flows out from there, ponds in this other level, and now it's breaching that area and starting to put these other flows across the crater floor. This was taken earlier this morning. There's another flow going off that way over there that looks like an flow. And even in this video, you can occasionally see chunks falling in the foreground out of the plume. Right? You can see the fountains are way below, but there comes some chunks across the screen. So even this far away, that's how those glove-sized chunks of rock that are very frothy and brittle can be flying through the air because they're so so light. Yeah, nice flow right there. There's another branch going up. So it was great to see this released so quickly after they filmed it this morning for them to put it out already within a few hours. That's what people are wanting. So fantastic. Most of us have been looking at this eruption from the other angle, right? From the far side of the crater, looking back in this direction here. So pretty cool to see it from this angle. All right, I will move on from that there. A lot of visitors coming to the area. This is a Kanakakoi overlook, photographed by the USGS in a pre-dawn hour here. See what that actually looks like. Right. Here's a view from Volcano House, how that looked in the early morning as well. Fountains and that lava pad in the far southwest. You can, of course, use telephoto lenses, and it makes it look a lot bigger, something like this. So you can really get great images from those areas, Volcano House and Kanakakoi in the south. And there's a wide-angle view from Kanakakoi National Park. So those of you who are not able to come or not able to brave the parking and all the traffic and all of that, there's just a little bit of a window into what that looks like. Right? And some other zoomed-in view from Kanakakoi, what the angle looks like from there. And then back to the west rim, where the rest of the USGS team or some others of the USGS team have a different angle, as we just saw in that video there. Setting up high-speed cameras, high-resolution cameras. Yeah. So one last thing I wanted to talk about visually here is this feature that we saw Let's put this back up here, right? This pattern that we saw in elevation. So before our current flood of lava in the current phase, we had this interesting signal right here. We see this is actually elevation, right? So meters above sea level. The one place laser rangefinder is pointing is near that old West Pond vent, the one that was circulating and the lava level would rise and fall, which is why it was useful to have laser elevation pointed in there. Everything's changed a lot since then, but we'll recap this a little bit. But in that area where the laser is pointing, we saw the ground drop down, then back up quickly, and back down and back up second time, and down and up a third time before doing some settling in response to that. So what was going on there and what would actually happen? And it's not hard to be, it's not easy to be conclusive about it here. But we can pull out this video. Here's a video that begins on the 13th from the F1 thermal camera. And right in here is a spot where this is occurring, where lava is being measured by a rangefinder. So if you look in there, that's what it looks like in a full crater, a tiny little spot overturned with lava 3 times right in there. And since that's small and a little bit hard to see, or here comes our current eruption, and you can see it actually comes and covers that area within the first day here. So let's zoom it in. Here's what that looks like zoomed in. There it is, 1, 2, 3 different pulses, and then it cools, and eventually comes to get flooded by lava. Yeah, so let me see if I can get this to another video on here. All right, so what I'm doing now is, I'm gonna pause it. It's hard to see, this is so zoomed in. This is now the KW camera. And what you have here is a very zoomed in view of, this is that old West Pond vent right through here. There's a lava would come out through these vents over here on the right and go through this little lava tube and then pour into the channel and then flow out back, circulate that way through this pond that was all through here, right? And so this is early on, we're back in mid 2023 here, but just point out what this area actually is. See, there it is. It actually gets uplifted with an eruption. You see some glow in that area. It's uplifting again some more, but there's a lot of cracking, degassing through this area here. Now we're in 2024. And here, from that area, is where you see one of these new vents actually pop up. When that first episode is over, lava withdraws and actually leaves this pit. So it looks like it's that same area once again. Second pulse comes through, pours in it again. You see it actually still glowing separately and fuming separately once again right through here, right? Now we're in our long pause, a 12-day pause in between episode 3 and 4, where you can see this area. There's a little bit of glow right through there. Oh, actually, so here's our 3rd episode, actually. So it was 2 and 3. And here you see lava pouring into the crater. And then actually, yeah, you see it actually all the way covered up, and you don't really see much indication on the surface that it's there anymore here in the middle of episode 3. Episode 3 is about to end in a couple of days here on the 3rd. So we see movement of lava actually stop. And it's going to pause. And let me fast forward through a lot of this pause here, because it's dark for 12 days. Still dark over there. Until, yeah, right in there, where we see that first, the 13th, that overturning and a collapse, right? So the pit reappears during this pause as a result of this, whatever's happening in here. So then here comes the lava coming and flooding across it again, right? So that's the KW camera view there. That reminds me a little bit of what we saw towards the end of our last eruptions at the summit, where we actually saw within a couple of weeks after the lava stopped flowing, you see overturning processes like at least one time later on. And so because this is actually over this area where we saw this vent pop up, and because it's over this area that we previously saw this West Pond vent with lava circulating, we knew that there are vents in that area, but it's a different spot on the crater floor than everywhere else, because we know that has a spot that went deeper and also has a deeper pit that it can flow in. So it's still not quite clear if it was something induced from below, like maybe the crater was starting to wiggle with a new eruption and pressure coming up. Maybe that dislodged some of the gas bubbles or caused them to coalesce. But even without that, you'd expect that over time, gas bubbles do coalesce and eventually build some critical mass that can one last time cause that surface overturning and disruption. after eruption is over if you have a deep enough column of it somewhere, like a pit like that, perhaps. So that's one possibility. The other being that the vent that cracked open through there as well, right, could possibly just drain lava back in the crack if that's a pathway that's still open. So not quite clear what's happening there, but really interesting to see that that crater seems to reform a couple of times in that same spot again and again. And this is something we'll have to dig into more in the future, since that's probably all the time we have for this imagery here today. We do want to touch on some of the monitoring, and it is worth going through a little bit of detail what the USGS sequence of this was. I will highlight some of these reports going back to last week. So last week, as we said, the USGS was doing their overflight. At that point in time, they are still noting that there's a pause. They do say, let's see here. That over the last 24 hours from Friday, there was persistent glow at the inactive vents, and that there was stabilization of the subsidence of that area. Yep. So that was on Friday the 10th. Then they fly over that morning, and as a result, they put out this information statement at 11:30 in the morning. They note that the volcano is still inflating, magma is accumulating in the area. They note that the style of eruption has changed to this episodic eruption style. That is something that hasn't occurred super often, but it has occurred before, most notably the beginning of the Pu'o'o eruption, the beginnings of the Mauna Ulu eruption, and the Kīlauea eruption as well. Each of those having, Kīlauea had 17 episodes, Mauna Ulu had 12, and Pu'o'o had 44. Just in that initial sequence of episodes, right? So they're saying that we appear to be in this pattern of eruption now, and not only that, episodic eruptions have a feature of repeatability, which allows patterns to be identified. So they actually noted that following episode 1 and episode 2, they needed 6 microradians of ground tilt, and at the Uikahuna tilt meter as a pressure threshold to resume the eruption at that point in time. They did note a little further on that because there was a large deflation and prolonged fountaining at episode 3, there might need more inflation to reach the pressure necessary, but that even still, they believed that a new episode could begin between January 8th and January 13th, when the tilt was expected to reach 12 microradians, about double of the prior increase threshold. So that was the smaller window. If you widen it a little bit, you might say January 8th to 15th, we'll say, right? So and then they basically got the tail end of it there. They were a little bit ahead of it with their window here as well. They do note this caveat, they're being a little technical here, that defining windows of time where there is a higher probability or likelihood of an eruption restart is different from more precise forecasts that state a time and an actual event that will occur, right? So they do know that the magma was near the surface, but not exactly how much of it was needed to be cleared to release the fresh magma below there. So that's was the information statement they put out on Friday, noting all different possibilities that when eruptions episodes begin, they have very high gas emission rates, up to 140,000 tons per day during that first episode. But that overall, the pattern is that after that initial pulse, you have fountains usually decreasing, and you have the drop to sustainable lower effusion rates, or a diminishing and ending of the eruption following that. So we're still early on in this one, at least in the context of episode 3, which was 8 days. Right, so we're past our 15-hour threshold of episodes 1 and 2. So more likely we're like in episode 3 now, and yeah. So we still have some more days to figure out which way this is going to go, whether it'll be longer lasting or not. So on Saturday, they noted lava was still close to the surface, right? But sluggishly just below the mouth of the vent there. By Sunday, they note that minor spattering begins to occur within a northern vent, right? Not consistently, but in several pulses. There are times where you actually could see lava coming out of the vent, and not in huge quantities, but a little bit, and just kind of clearing its throat a little bit there. So that was the beginning signs besides the glow. So on Monday, they note that glow continues to be persistent. There's less spattering than the night before, right? And come Tuesday, they note the subsidence that we just looked at on a thermal camera there. And they say that might suggest the magma column has withdrawn deeper. But in counter to that, there is still unchanged glow from the vents, showing lava was still near the surface there. Right, so that's why I might personally favor the idea of it overturning within a deeper pit than it being withdrawn through the magma column, because of what they say here, that they still see lava close to the surface at the vents when this occurs. Seismicity was low. Everything else was low. They did track all this as well, the times that they occurred down through there. But in the interest of time, we'll move on here and show you that Wednesday, they then note that the fourth episode had apparently begun. They noted a small lava flow exiting a north vent, following continuous low-level lava spattering that started earlier that morning from the same vent. At that point in time, early on, everything was at only the north vent, but by later in the day, the south vent would also activate as well. Right, so I'll keep it rolling, because after that initial update from Wednesday, there was also a status report on Wednesday, just before 11 a.m., where they noted that lava flow activity increased by 9:50 a.m., fountaining at 9:55 a.m. At the time, 10% of the floor of Hawaiʻi was covered with new lava, with a fountain about 200 feet or 60 meters high, something like that. And at that point in time, still no signs of activity at the south vent there. They note a tilt meter starting to level off. So one thing that's interesting is whether when lava is coming out, is the ground still swelling, or is it actually relieving the pressure that's coming out? And so at the very beginning, it's still pressurizing, but fairly quickly they see the tilt turning around to start to show pressure release signals. And that's what we're currently still seeing now. And you expect that things continue flowing normally as they are until that changes, right? If you see the pressure start to change, then maybe the fountains are going to be blocked off and turn off at some point, right, within this episodic pattern here, but not there yet. Just something to watch for over the week here. So they do note, if fountaining continues, it's possible that fountain heights will increase with more gas-rich lava. They can't guess how high. They did note prior episodes over 200 feet high. So that's the context for the update that we have then today, where they note all those same things. They know that the south vent became active around 11:40 a.m., also with lava fountaining and associated flows. They noted field crews reported fountain heights of 295 to 330 feet, or 90 to 100 meters from the north vent, and the south vent a little shorter at 40 to 50 meters, 130 to 160 feet. Both fountains were active overnight. The north vent consistently higher than the south vent. Closer to equal this morning at 160 and 140 feet. But at 8:25 a.m. today, parts of the south vent collapsed, resulting in a reduction of about half of the fountain height in the south vent. And here's where we note there's reports of Pele's hair falling on nearby communities, specifically at the Volcano Golf Course subdivision this morning, up through there, right? So that is where that comes from. All the other instrumentation pattern is as expected. They estimate the SO2 emission rate was approximately 10,000 tons per day yesterday after the start of episode 4. So that's what we're reflecting as the main hazard, is the Pele's hair and the gas here. So that's the text updates we have from the USGS here, as well as a map we showed you guys already. And I'll show you what that looks like here in the signals. There is our elevation, earthquakes dropping down, and our tilt has been decreasing here since this eruption actually began. That's the most important thing. That's the summit. There's a rift zone also decreasing, following the little wiggles we saw last week. There turned out to be just little minor adjustments, right? Earthquakes haven't done anything that different. It's just a result of the building pressure. Even if we do see the south flank moving in response to the volcano filling, right? It's just filling, and the whole thing is pressurizing and sending those pressure signals further out from the summit. But the fact that earthquakes are stopped and contained within the summit, within the magmatic pipeline, which goes like this, right? That's how the pipe actually goes. And within that area, they're only within here. That shows us that we have a blockage out through here, and the pressure is really from the center, which is why we see the eruption resume at the summit here. So that's really it. Here's our summit elevation for us to refer to. There's a little wiggles where 3 subsidences and our current increase there. Earthquake counts still fluctuating. And yeah, similar patterns across other tilt meters across the island. And I'm just going to scroll through here just because we usually look at all this. Nothing has really changed that much on all these other signals here. All right, so there's a couple final things. Volcano Watch has been put out. This is the one from last week where they discuss a pressure within Kīlauea and pressure for volcanologists to foretell what's next. And to their credit, they did put out this possible restart window, which maybe you don't need to have an exact date and time, and a window is good enough, I would say, right? So great to see this put out, and there's more information on this posted online. And another one was issued today, peering into a crystal ball, where they release some images of the September 2024 Nepal eruption, how they note different magmas mixing result in different textures across the crystals in microscopic scale within the lavas. This is plagioclase crystal. And here an olivine crystal from the more recent summit eruption, all through here, right? Which the long and short of it is that they say that they have typical summit eruption compositions in the summit, right? But with a couple different textures suggesting there was maybe an influx of magma coming into there. This is also posted online with that key, the key statement here is for episode 1, mostly typical compositions. However, some minerals show differences that could suggest transfer of magma from multiple magma storage regions. So that's all we have so far. They're analyzing it still. And just to recap on why I'm rushing so much here, I will mention that the Volcano Awareness Month for the USGS continues, as we have here the schedule. And today is the geologic mapping, the art and science of geologic mapping by geologist Stu Drowns at the Volcano Art Center. So while there might be more to talk about and more to show, I will skip showing any earthquakes or kind of similar slow pattern. We'll just skip Mauna Loa today because we are out of time as well. And what have we got here, Dane, before we transition over?
So I'd just like to, take this little opportunity to give thanks to the Puna Strong and Kilauea grant programs through the County of Hawaii and the Hawaii Community Foundation for helping to provide funding for this program, as well as their other programs of digital resilience and youth development. Their support really goes a long way. We also like the support. Thank everybody that has made donations over the past bit. I don't have a list up in front of me today, but we really appreciate that. Donations on the HVERI website through hveri.org/donate is where we prefer to take donations. We also do take super chats, but prefer the website. And other than that, we are just kind of at this point waiting for Lou. I can add that to the stage. Oh, why did that happen?
Yeah.
I was trying to add the stream to the stage and it went somewhere else. So I'm not sure what that was about.
Yeah, we probably have to set up the layout for that. Yeah. He's not a.
Okay, so we'd have to do our sign out basically for me and you, and we'll keep the. I think the ASL team is going to stick around, and we can put them on. Is that?
Yeah, I'm not sure we have a scene set up for this. Is what I'm saying right now. Yeah, I'm not sure.
Okay.
Let's see if we can set this up here to get Lou ready for what's coming on.
So yeah, I'll go ahead and just continue talking a little bit. So tonight's presentation is by Drew Downs. It's going to be on the art and science of geologic mapping. So if you're into the GIS and that whole domain, right, this would be one of the talks for you. And Mike Zaller from USGS is also doing some talks, similar vein. Right. So yeah, we're just trying to get the stream set up at this point to be able to bring this event to you live and transition off once we get started.
So we do a number of in-person events around the island, guided walks and talks. And so I'm really happy to have Drew Downs here tonight. He's a research geologist at the Hawaiian Volcano Observatory, and he specializes in investigating the collective history of volcanoes and constructing geologic maps, which we'll talk about tonight. Drew is from Illinois and has a bachelor's and master's from Southern Illinois University and a PhD from the University of Auckland, New Zealand. And he's worked on volcanoes in New Zealand, in California, in Saudi Arabia, and of course here in Hawaii. So, yeah, maybe he'll talk about that tonight.
And you will see some maps I've made of those volcanoes. So,
thank you, Drew.
Yes. Good genes.
Love hiking.
Well, thank you very much. And hopefully, just before we get started, I'll make sure like the lights, everyone can see the screen okay, and the microphone's okay for your live stream. And just a reminder, Katie, apparently you got to change the sound every like 15 minutes or it'll go blank. So we'll get started. Just curious, since we're not at the After Dark in the Park at the usual spot, does everyone live up here? Is there anyone from off island attending? I recognize a lot of faces. And all right, so we've got a group from mostly on island, it seems like. Uh-oh. And for some reason, it is not advancing. Oh, wait, did you do that or did I do that? Okay. So this might go smoothly and it might not go smoothly. So my talk is titled The Art and Science of Geologic Mapping. It might be better titled A History of Geologic Mapping. There will be some talk about how to compile maps, but a lot of what I'm going to be talking about is kind of the history of the USGS and its mission, as well as kind of the earliest maps, what they contained, and progressing through time as to what these maps look like. And you can see here I have a very nice map of North America there that is color-coded by the age of its bedrock. So we'll get into more detail kind of specifically on what this represents, but you can see here's where I grew up in this blue swath that covers a big part of Middle America, but then you get into the mountainous regions which are more chopped up, and this all means different things, but in essence, what a geologic map is you're going out and you're seeing what's on the ground. So two of these pictures are from Hawaii right here, the Southwest Rift Zone. If no one's ever been here, this is the lava plastid cones. This is the 1823 eruption riding up over an older cinder cone. And then this is just an aerial view of the Southwest Rift Zone. You can see different colors of rocks that probably represent different eruptions that we draw as different units on a map. And to get back to Saudi Arabia, this top picture is some of the work I did in Saudi Arabia. And as you can see, it's quite an easy place to map. There's not a whole lot of vegetation, much like the Southwest Rift Zone, but unfortunately, Frank Truesdale isn't here tonight. He could probably tell you a lot of stories of trying to map the East Rift Zone and all the bush they had to go through to get that accomplished. So getting started, kind of our introduction. What is a geologic map? Well, the definition I put down might be very simplistic. It is meant to show geologic features. Okay, well, what does that mean, geologic features? There are several things that go on a geologic map. The obvious one, rock units and strata. Strata are just layers of rocks that are on top of each other. So basically, what we're doing is we're taking a map, usually a topographic map, a contour map, and we are drawing rocks on it. It also has linear features. So for Hawaii, some of the big ones are fissures, ground cracks, fractures, faults. Some places you get a lot of folding or bedding plains. These are usually in areas that have more, say, sedimentary rocks like sandstones, limestones. They're, laying down gradually on top of each other, and you get these plains of beds that you can measure. And then you might have points on your map, samples, places where you find something you think is important and you want to take a description of. And as it says here, typically overlain by some sort of topography. So contours, or in this case, this is on a digital elevation model of the entire world. So this is kind of the same map that was shown before for North America, but extended over the entire world. And you can even see they've got the oceans color-coded in here. So here we have the Mid-Atlantic Ridge, a big mountain chain under the Atlantic, and they've kind of guesstimated what the age is of the seafloor basalts that are kind of lining these regions. And that's probably a talk in and of itself how they did that, but that goes back to in World War II with sonar and magnetics, where they were able to measured different magnetic susceptibilities on the ocean floor across these mid-ocean ridges to get how, they aligned, and that's how that mapping came to be. So continuing on with our introduction, this is where I grew up. I had to put in something of Illinois. Maps, as I said, show rock units and strata. How many people have been to Illinois? How many rocks have you seen in Illinois? A few? A very few. In fact, the rocks on this map are this white unit down here. So, but as you can see, I've got two maps of Illinois here. I've got this colorful one here and this slightly muted but also colorful one here labeled Bedrock Geology of Illinois. I can tell you, I grew up right in the middle of the state right there, and there's not a rock to be seen unless you hit it with a tractor. And you know where that rock came from, probably Canada. Yeah, so all of this is glacial outwash. So as I say here, rock units or strata, it's something we put on a map. They make up our geologic units. So our geologic units, they tend to be things that have what we call similar lithology. So something like if it's made of sand, a sandstone, similar lithology, limestone, or in Hawaii, we have basalt, lots and lots of basalt that we can map. Sometimes you want to do it by age, maybe by composition, as in, again, Hawaii, maybe you want to make your map by different types of basalt. A lot of people will run chemistry, so maybe you want to map that this unit's got 5 weight percent, magnesium. This one's got 7, so you make them different units, or some sort of defining characteristic. A lot of these maps are like this one. You don't care about the soil or sediment on top that's loose. You care about the bedrock. But some areas, you get really thick deposits on top, so it's hard to map the bedrock. That's where this map comes in. This is a superficial geology map of Illinois, and this is all the glaciations. So you can see here, this green unit is a glaciation, this pink unit is a different glaciation, and where I happen to grow up, you've got about 500 feet of soil, sand, and other loose material on top of the bedrock. Well, you might ask yourself, well, how do you get a bedrock map of Illinois then? That seems a little difficult. Well, maps are made because there's something special or important to the region you want to know, you want to be able to map out. Illinois, at least back in the day and slightly now, is well known for its coal and oil deposits. So where I grew up, was a coal mine. There was a coal mine disaster in the 30s that the mine blew up, killed about 50 people. But that was one of many coal mines that were throughout the state of Illinois. Illinois is also a basin, so there's now a lot of oil and gas drilling that goes on. And that's actually how this map was made, from drilling and coal mines burrowing under all this loose sediment, and they were able to put together a bedrock map that looks like this. So large portions of the US, you might have to do that where, you've just got way too much stuff covering your rocks. Maybe. Oops, I think I went too far. No, I didn't go too far. I'll try not to skip anything with this thing. And this is just another type of map. So in Hawaii, we've got an abundance of rocks. In fact, they're almost all basalt. But this map shows different basalt. So in this case, this is the new map that Dave Sherrod and others put out, which is the geologic state map of Hawaii. I'm just showing the one that has the big island on it. And if you were to map all these eruptions based on composition, this map would be very boring. It'd be almost all the same color because almost everything is basalt. But they did this by eruption. And to make it easier to read, they've got Kilauea in different shades of red and pink. They've got Mauna Loa, which abuts it, in different shades of green, Hualalai in different shades of kind of reddish, orangish. And this is just one way to put together a map that you can show different units that might even be the same age, but you're able to tell them apart. And before we get too far, I want to talk about map scale, because if we go back real quick, the scale on this map, which you can't read, is probably about 1 to 100,000. The scale on this map, which I also can't read, is probably slightly smaller. But scale has everything to do with kind of the detail you're able to see on your map and what you're able to show. So in this case, Down at the bottom here, if everyone can see, this is Atlanta. As we zoom out, this is the state of Georgia. This is the southeastern US. This is the whole US, all showing Atlanta on them. All at different scales. Also, you can see different detail on the map. So if you're zoomed in just on Atlanta, you've got a large scale. So you can see lots of detail. If you're zoomed way out to the states, that's a small scale and you don't have much detail at all. So that's kind of how scale works. The further you're zoomed out, the smaller the scale, the less detail. The larger you're zoomed in, that's a large scale, but you get a lot greater detail. And you'll often see these on maps where somewhere it'll say scale and it'll have something like, oh, 1 to, in this case, 15,000. This is just an arbitrary one that I made up. And you might think, well, what does that mean? Well, that's supposed to be a conversion unit for your measure. So say what I put down here, you find a road and you measure it on your map and it's 3 inches long. Okay, what does that mean? Because if you go out in the world and walk that road, it's not going to be 3 inches. So what you do is you can take that 3 inches and you multiply it by your 15,000. So that gives you your 45,000 inches. So that 3 inches on a map, if you walked it, is 45,000 inches in real life. Well, that's not very useful for most people. You might wonder, well, I don't measure in inches when I'm walking around, but you can do the conversion if you love math that much, and it comes out to about 0.7 miles. So that's what the map scale is on a lot of maps that you'll find, especially published by the USGS. What are the tools we use? Well, basically the same thing that's been used for a long time. So you can see me here. This is actually a now late colleague, Dwayne Champion, who I don't know if anyone ever had the chance to meet him, did a lot of work in Hawaii. He passed away 2 years ago, sadly. But we are using here the same instruments that are up here for the most part. He's holding a GPS. I'm writing notes for him. But we take out hammers, we take out hand lenses, we take compasses. Usually we have some sort of map reference, a topographic map, so we can figure out, sometimes I take a chisel, but definitely a tape measure, markers, bags. I usually don't take this. Does anyone know what this is? This hydrochloric acid. No, exactly. Not very useful in Hawaii. So this is actually used to test sedimentary rocks a lot. You dump it on limestone, it fizzes. It reacts with the limestone, it fizzes. Say you're confused if it's a sandstone or limestone. If you pour it on, you're going to figure out what you've got. So these are the tools we tend to use, and they've been the same for hundreds of years, 200 years or so. They're very similar. So now we're going to jump into some of the oldest maps and move forward. And this is the oldest surviving map that is known. So this is the Turin Papyrus map. It's from Egypt, and it's thought to be created around 1150 BC. And much like maps today, it was made for a specific purpose. The pharaoh, Ramses IV, wanted statues of himself made. Well, what are you going to make these statues of? The best material they had was sandstone. So someone went and found sandstone, and they had to tell someone to go quarry it and bring it back to make statues. So they made a map. And you can see here, it's kind of hard to tell, but what's immediately noticeable about this map? Large scale, there's a lot of detail on it. There's different colors. You can see here. And you can still go out in Egypt today and find this same kind of detail. There's these darker colored mountains, and then here it's kind of hard to see, but there's these more pinkish colored mountains. And then you can see this kind of snaky line going through it. That's actually a river, and the little bits in it are river gravels that they mapped. And I don't know which is which because I don't speak ancient Egyptian hieroglyphic, but one of these probably up here is the sandstone quarry that they found and were working. And another one is a gold mine from the region. A gold mine, yep. And this is the oldest surviving map that is known. Now we're going to jump way ahead in the future. to kind of the earliest modern geologic map, which is made of this region. And you'll all have to pardon me. My French is horrible, so I'm going to have my lovely wife pronounce this guy's name. And this region. All right, I can't say any of those things. So this is a Frenchman who, in central France, mapped this area of the Chaîne des Puys. And this is a extinct volcanic area. And he kind of made, maybe, this map. And you can see it's kind of got some pinkish colors to it and different units based on, pinks and black colors here. He's got a lot of detail as far as the topography that he drew in. So this isn't drawn on a topo map or anything, but he was able through his drawings to kind of mimic the landscape and give it a texture that shows what the topography looks like and what the different volcanic units look like that he was mapping in this region. We're going to jump further forward a little bit in time to the US. And this is the first known geologic map of the US. So this was created by William McClure. It was put out in 1809. And he spent a huge amount of time, or at least for 2 years, he spent all of his time going back and forth through the original 13 colonies and making a map of 5 different rock types, which has stood up surprisingly well. Of course, you can get down in the nitty gritty and pick apart different units in some of these that he made. But on a regional scale of the eastern US, this map actually still stands up pretty well as far as his different rock types and the units that he ended up mapping. But not long after him comes the real big name in geology, William Smith. And there's a very good book on this guy called The Map That Changed the World by Simon Winchester. I would highly recommend it. It's very entertaining. But he is the first person to map an entire country. So he mapped England, Wales, and only part of Scotland. He led a very interesting life. Making this map was kind of his life's goal. He thought he'd become very rich and famous from it. He did become famous as far as geologic circles go. Rich, not so much. He spent a lot of time going into debt. He was in debtor's prison in and out for a while. But he ended up making a very detailed map of the England, Wales, Scotland, and ended up developing what are principles we still use today, putting together maps called Smith's Laws. And these laws help determine kind of the order that we put maps in that strata are laid down in. So kind of if you look at a map and you say, oh, how do I know this is older than this or this is older than this? He's the one who really developed these laws. And he did this as a canal worker. So he was an engineer. He oversaw a lot of digging of the canals in England. And he'd go through and he'd be like, oh, I've seen this black shaly unit before. I've seen this sandstone unit before. And he'd go around to all these canals that were being dug throughout this time period in the UK. Well, not only that, but this black shaly unit, I see these shell fossils in it. But I don't see them in this one over here, but I see them in this one over here. And this one, they're here, but divided by sand here. And he was able to use this to correlate different units throughout the entire country while he was making these maps. So the different laws he came up with, one's called superposition. And it seems very obvious when you think about it, but if you have a layer here and another one here, well, the one on top has to be younger. I mean, very simple, but no one had really come up with that idea before. And then his other one was based on his fossils. And that is, okay, if I see these distinct fossils here, but I can't find them over this unit or over this unit, I can use that to say this unit with the same fossils over here is the same age. And that's how he ended up being able to put together this map. We're going to jump to the USGS now, because not long after this, about 30 years or so, the USGS came into being. And the USGS has a strong mandate for making maps. And that has evolved from its inception to now. It's gone through several different cycles of, what maps should we make? What use are they going to be? And there's a lot of different uses for maps. I mean, a basic one is just understanding the history of the Earth. That's kind of the academic answer of, oh, why do you want to look at it? To figure it out. But it's a lot more complicated than that. When someone says, well, if I want to pay you to make a map, I want to know what it's worth. And a lot of this, groundwater quality, earthquake, landslide, volcano hazards maps, flooding, minerals, energy resources. You want to build a city, you probably want to know what you're building on, as well as ecosystems and wetlands. And I've got just two here as examples. You can probably tell this one is for economic purposes. Major nickel, copper, and platinum group element deposits of the world. So all things that are very important that people kind of want to know, well, we use nickel, we use copper in a lot of things. Where are they? Where might it be economical to continue looking for them for mining purposes? Or in this case, a lot of you probably can't read what that says. This is a hydrographic map. So these are aquifer maps. So, there's big white portions here, especially up in Alaska. A lot of that's probably because if you're going to map an aquifer, it's hard to just look underground and see. You need to have a well. So there's large parts of the US that don't have wells in them, but there's large parts that do, and map out the aquifer, and you can tell which aquifers are plentiful, how thick they are, or if they're being diminished. Especially California is worried about that as their aquifers start to dwindle with all the groundwater mining that's going on. So back to the USGS. It was established in 1879. And this is a first director of USGS, Clarence King. This is our second director, John Wesley Powell. The kind of mandate of the USGS was classification of public lands and examination of the geologic structure, mineral resources, and products of the national domain. Now, this is really, John Wesley Powell took this, a couple steps, and he's kind of the most influential director that the USGS has ever had. I put Clarence King in here because he is just an interesting man. And I want to give an entire talk on him, but this is not the place or the time probably. But just a brief backstory on Clarence King. He was only director of the USGS for 3 years, but he had a long history of kind of, Western exploration. They did what was called the 40th parallel transect, going out to California to the coastline and kind of mapping the resources. How he originally became really famous, though, was that there was a couple unscrupulous people who were out in kind of the Northern California, Nevada area, and they said, oh, we found all these diamonds. We're going to be rich. Invest in our company. Well, it's all a scam. He went out there and he said, no, there's no diamonds out here. This is all a scam, and it all fell apart. And he became really famous that way. If anyone's ever been to Sequoia Kings Canyon National Park, named after Clarence King, but none of that is even remotely close to the most interesting stuff about him. He led a double life. So by day, he was this eminent, famous geologist. At night, based on the reports, he liked to go what would best be called slumming with the poor people. And he ended up meeting a woman named Ada Copeland. And in this day and age, a relationship with Ada Copeland would be fine. For Clarence King, it would have been a little weird and difficult. So Ada Copeland was a black woman in the 1880s. He was a white man. It was very much frowned upon. So how he got around this was he convinced her he was black. Now, as you can see, that man looks very similar to me. But at the time, this wasn't questioned because, he's just like, oh, well, my great-great-grandfather was black, and, who would want to pretend to be black? So this is what he did. Ended up, and he told her his name was James Todd, not, Clarence King. He ended up marrying her. They had 5 kids together. She knew him the rest of his life as James Todd until his deathbed, where he confessed, no, my name is Clarence King, and that was that. So he ended up dying in 1901. She lived to be 103 years old and didn't die till 1967. But yes, by all accounts, a very strange, interesting man. I find him so fascinating. But the more influential man was John Wesley Powell. So he took over after Clarence King was in charge of the USGS for 3 years. John Wesley Powell, in his own right, is a very interesting man. He fought for the Union during the Civil War, staunch abolitionist. He actually fought for the 20th Illinois Infantry, my home state, and ended up getting wounded in the arm, had it amputated above the elbow, but then went on to do several whitewater rafting trips down the Colorado River, all at a time before any dams were put in place, of course, and by all accounts, a very hazardous trip, and did a lot of work as far as trying to control Western expansion in the US. If it was up to John Wesley Powell, the arrangement of states in the Western US would look very different today than what it is. He actually wanted states to be based on watersheds, not these nice straight lines and squares all over out there. And he wanted the Western US to be populated very slowly, because after his time out there, he saw, well, this is a desert. I mean, how many people can it actually support as far as agriculture goes? Things didn't quite turn out that way, but he was very influential as far as how the US was going to go about inventorying its public lands. And what ended up getting passed is the Organic Act, which mentions geologic and economic mapping. And he took this and latched onto it, and he's like, we need to map the entire US and find out what resources we have. So what ended up starting is what's called the Folios series. So he wanted to make a geologic atlas of the United States. And they were going to do this quad by quad for the entire United States. And it was to have a standard format. So every place in the United States was going to have a topographic map like this, contour lines, a geologic map, and other maps of things of interest. In this case, very much focused on economics, what's useful to the United States. And then, of course, a pamphlet like this that kind of outlines in the text what all this means. So this is one of the original maps. This is the very first one that was put together near Livingston, Montana. And this was probably started because at this time, does anyone know what Butte, Montana is famous for? Copper. Butte, Montana is very close to this area. In fact, at one point, there's a copper deposit there. It's called the richest hill in the world. In fact, there's a great book on that called The Battle for Butte, where miners would occasionally, mine into someone else's shaft, and they'd get in fights, and quite a bloody affair at times. So this is probably why Montana in this time was getting some of these folio series going. Maybe. So, well, jumping ahead now. They are. So this is the geologic map. And you can see, again, this is kind of similar to what geologic maps today even look like. They're nice, colorful for different deposits of different lithologies and different line work for, just typical things you see on a map. So this is the geologic map, or as they call it, the aerial map. This is the economic map. And you can see here it's got a slightly different symbol up here, and this line gets a bit darker. And the thing they found here that was of economic importance to them was coal. So that was the only thing in this folio sheet that they noticed that might be economically important to the United States. And then a final thing they did was they wanted to know the structure. Well, to get at the structure, you can look at the map, but if you tip that map up on end and say, cut it, like if you were to take a section of rock, cut it vertical, and look in it, you'd get what these things are, cross sections. And they can help you kind of see in 3D what the structure is of a certain region. So here you can see they drew a cross section across here, and you can see different folds here. Or for this economic deposit, they can tell it's kind of dipping off to the north there. So if they wanted to mine coal, Well, it's at the surface or close to the surface here, but out here it's probably much deeper and harder to find. So this was started, the first one was published in 1894. Oh, I believe this is supposed to be 1904, not 1804. They had 106 folios done, the last one being published in 1945. Well, 106 is not even close to getting a map of the United States. But economic crunch, they're like, is this really worth the time and energy that we're putting in it? This is the last one that got put out in 1945, Pennsylvania. You can see here on the topo map some nice folded structures. So out getting close to the Appalachian mountain chain. And in this case, this is our geologic map. Again, you can see overlying the topography here. They apparently didn't find anything of economic value because there's no economic map to go with this one. Either that or they just stopped publishing economic maps this late. But there is a structural map, and you can see here the nice folded beds here that are running through kind of the structurally complex area. But after the folio series ended, I mean, the USGS was like, well, we still need to make maps, but maybe the right approach isn't just going quadrangle by quadrangle across the US and doing this. Maybe we should take a more targeted approach as to what's important to the country. What are our needs right now? So some of these, more specialized mapping for economics, again, hazards. So the mapping, the reasonings are kind of staying the same, but it's like, well, instead of, just this preset area, why don't we pick the areas we think are most important? And some of those maps, particularly as we get in the Cold War, nuclear waste treaties, Wilderness Act, mapping out wilderness areas and what's useful in them, what should be designated wilderness. This is one of those maps that came out of that time. As you can see here, this is Yucca Mountain. I assume everyone knows what Yucca Mountain is famous for. The nuclear repository that was built and has never been used. But of course, before they built a nuclear repository, one of the things they wanted to know is, well, if we put it here, is it safe? Is it going to contaminate groundwater if something spills? What if a volcano comes up underneath it? What if a big earthquake happens to cause, a cave-in or anything like that? So what they went through, they mapped this area where Yucca Mountain would be placed. They wanted to know all the faults. They wanted to know the type of rock. I mean, you don't want porous rock that's got groundwater pouring through it, so they picked something really dense and granitic. There are also semi-young volcanics in this area. They wanted to know, where are they? How old are they? Is there a chance of an eruption again? Turns out very much likely, probably not. And then there's maps like this. This is a hazard map, and as you can see, this is a very plain map. Most of this is just right here, kind of the pinkish color back there, contour lines. And then you've got all this gray. These are landslide deposits. So say you want to build a town somewhere or a factory or run a road through or power line. It might be good to know what areas have had landslides in the past and might be susceptible to landslides in the future. So these are some of those more targeted maps that were getting made. And then there's maps like this one, which is the summit region of Kilauea. And of course, anyone who's been to Kilauea recently knows it erupts a lot. So having a map showing where our different eruptions are, how extensive they are, where the vents tend to open, are all very important. And Hawaii itself is one of the most mapped places. And as you can imagine why, it has a lot of eruptions. Every time you have an eruption, there's something new to add to a map. Now, not all of these go on, fancy printed map sheets like this, but a lot of them are put on our website and easy to access. But we're going to move more into volcanoes now because we live on a volcano. This is Volcano Awareness Month, so no more maps of Illinois, as much as I'd like to show them. I was actually a little disappointed. I was trying to find a map of the county I grew up in, but there's nothing. So there's a whole statewide map, but nothing of the specific county. So there's as you all know, there's a lot of different types of volcanoes. So we live on a shield volcano here, which has a hot spot that's feeding it far from any plate boundary. Whereas the Cascades are more like this. So you've got the Pacific Ocean hitting North America, going underneath it, generating heat and magma, and you get these big, tall, kind of more pointy volcanoes. And they do tend to make different deposits that are important to map out if you're worried about hazards. So for Hawaii, do we get tephra and explosive deposits that can be thrown in the air? Yes, but not as extensive as, say, something from Mount St. Helens. So not something we're worried about as much as we are lava flows and where fissures might cut through. And I'm going to start by showing some Saudi maps, and then we're going to move back to Hawaii. So these are just some of the different features in Saudi that we had to map. You can see a lot of these are grayish tan rocks. They're a lot more silica rich than they are here in Hawaii, so they tend to be a lot more explosive. These are not per se like the Cascades, but they're not quite Hawaii either. They're kind of in between. So there is a rift there, and it causes, you know, heating magma to come up, and you get all these little cones that pop up in places. And I just like a lot of these photos, which is why I threw them in. But you get these domes and spines sticking up. You get these more cone-looking features, as well as these big, broad craters that throw out explosive material. And these are all from this area up here. So this is Medina, one of the holiest sites in Islam. And it sits right, it doesn't actually sit in the lava flows, it sits right between some young lava flows, but it's part of this volcanic field that runs 300 kilometers, so about 200 miles north-south, about 50 miles east-west. And this is how I was originally brought on to the USGS, was the Saudi government had hired the USGS to come over and do a hazard assessment. Well, to do a hazard assessment, you have to know something about the rocks. You can't just go, okay, we'll do it. And the best way to do that is to make a map. And you can see here this breakdown. There's been people who have worked out there since the 80s and kind of tried to piece together the different strata and lava units, but not a whole lot's been done in the last 40 years or so. Oopsie. Okay. I don't know how. Can you just forward for me, Katie? You all get to see it a second time. Oh, a little too far. All right. Oh, wait. Too forward. Go to the next one. Thank you. So this is part of the mapping that was done for that northern area. So this is about 60 kilometers by 50 kilometers wide. So let me try and do some math, and we'll say 30 miles by 20 miles wide. And this is just based on age. So if you want to do a hazard assessment, you need to make a map and you need to come up with ages for these rocks. So we collected a lot of rocks and we did isotopic measurements on them, which helped us get an age. And that way we know, where the young eruptions have occurred, where the old eruptions have occurred, and you can kind of get a sense what might be more hazardous to build in. In this case, you can kind of see these darker purple, blue colors are the older things. There's not very many. There's some purples down here, over here, a little one up there and there. And the blues are around the margins and a couple interspersed in the middle. Then your middle ages, you try and, I've got in green here, and you get a lot more of those that are exposed. But our young stuff are in the red and oranges. And when I say young, this is not young like Hawaii, where, you get 9 eruptions in 4 years. Most volcanic fields do not behave the way Hawaii does. The youngest eruption here is from 1256 AD. And then the next eruption from that is probably a couple hundred years older, but technically it's still considered an active volcanic field. So it is something that, in the next tens, hundreds of years, there might be an eruption, and could it impact the city? You can see the road here. This is the main ring road around the city, and about 1.5 million people live within it. And the youngest eruption sits right here. In fact, Their brand new airport that they just built sits right here at the very end of that lava flow right there. So right here is where we've got the youngest kind of vents and lava flows radiating out. Down here, you'll see some young stuff too. This is the more explosive eruptions. Luckily, the deposits don't make it too far, and no one lives out in that area. It's just kind of desolate desert. But the one thing that is out here is the water supply. So they drill a lot of wells out here and pump the water into town. So even though it's not very near a populated area, it could impact the people in the city because the water's there. This is that same map, but in a slightly different scheme. In this case, I'm doing it by composition. I want to know, is there something special about these eruptions? Well, you can see all these tan colors. These are very similar to what you get in Hawaii. These are basalts. And most of this volcanic field is basalts, runny lava that goes all over the place. You start getting a little more sticky when you start getting into the kind of the greens, which is Hawaiiite, named after Hawaii, of course. Mauna Loa, or not Mauna Loa, Mauna Kea has a lot of Hawaiiites that have erupted from it. And then even more sticky as you move up into the blues, into the oranges, and then this is actually backwards. But the reds should not be basalt. The reds should be up here. I should have checked that before I put it in. And they're the ones that are explosive and throw out a lot of ash. So just another way of looking at a map. The first one by age, this one by composition. And if we, zoom in, I forgot I had this slide in. You go back, Katie. Sorry. That's this area down here in red. So this is not just one eruptive unit. This is actually several, but they're all the same composition. Oops. So this was all that area in red to the south. But as you can see, we've now got a lot of different colors. There's been a lot of different eruptions from this area. They're really explosive and have ash thrown out. And you can see here, this one came from, this kind of teal color came from this crater, this green one from this crater. This dome here created this red unit, and this really extensive orange one came from this caldera structure right here. And we can pick those out kind of with more refined chemistry. So we all know from the chemistry that this is all an explosive type, but there's some trace elements we can look at that are slightly different, and we can say, oh, well, we've actually got 4 different explosions here. And then these blues and grays here are all just the basalts that I was trying to filter out to get at these explosive eruptions. But when we put it all together, we get a map like this. So to compile this map, we did 7 months in the field. We collected 800 samples for chemistry, 180 cores. So that was drilling to get the magnetics of the lava, because some will have different magnetics and you can tell them apart. 155 plus 10 more, 165 different ages, and then isotopes from 75 different samples. All to put together this map of this, 60 by 50 kilometer area that tells us we probably had 250 eruptions around this part of the volcanic field over the last 1,000,000 years or so. So not super productive, not a Hawaii, but we do have some young things that are around the city center here, and you might want to be careful where you build. And those all can go into making a hazard map, which I didn't make, so I didn't put in here, but I can ask a colleague if you really want to see it. And also, we can get a sense of what's going on under the volcanic field. So as I showed you with the cross sections before, this is just a more cartoony cross section that we put together. Here's the volcanic field. And in that southern area, we have the trachytes, so like Pu'uva'ava, kind of more explosive ash generating and dome building. Whereas in the north, we get more runny basalts. And we can kind of figure out from the chemistry and the other data we collect, where this is melting, how much is melting, if it's stalling and what we'd call evolving in the crust, so going from a basalt to something more sticky to erupt, or if it's just a regular basalt coming all the way up and erupting. So we can take that map and kind of look in the earth and get a sense of what's going on. Now we're going to switch gears again, and I'm going to focus the rest of the talk on Hawaii, because who doesn't want to see Hawaii? So, as I said earlier, Hawaii's been mapped a lot. It's been mapped over and over again, and this is one reason you can see why. So this is part of the eruption that occurred in 2022 and filled the part of the caldera floor. And you can see here, you know, the lava just marching up day by day, week by week, and, you know, anyone who's been out there can see new flows are covering old flows. And it's such a dynamic place. It's a special place. It's very dynamic, but it needs a lot of attention for mapping because things get covered so quickly. I showed you that map that Tina Neal and Jack Lockwood made a little earlier. Well, that's completely out of date now because, of course, what happened in 2018? The caldera collapsed. And what's happened since then? We got a water lake. We've had multiple eruptions that are filling it in. We've had an eruption in the Middle East rift zone since then. We've had an eruption in the upper Southwest rift zone, all in 4 years. So it's a very dynamic place that is constantly needing the mapping updated. And this also feeds in then to hazard efforts as to, okay, where's our next eruption going to happen? Well, the summit seems a likely bet. It's been erupting an awful lot. This is one of the very first maps that still exists of Hawaii. And of course, you can see here the new chart of the Sandwich Islands, including Oahu, where Captain Cook was killed on Sunday, the 14th of February, 1779. So, you know, you can see the outline here of where their ship ended up going on this trip, and a general outline that does resemble most of the islands. He even phonetically wrote down a lot of the names that he was giving. So Maui, Hawaii, Morotai, you know, Oahu up here. Oahu is actually the only island that kind of doesn't really resemble the shape it actually has. But he did a pretty good job of being able to pick out, you know, the main mountains. Mauna Loa there, Mauna Kea. Kilauea is missing, but, you know, it's low on the horizon, easy to miss when it's dwarfed by these two. So this may not have any lava flows on it, but it's got a lot of information as far as place names, mountains, topography, the outline of the coast that would be built on by later mapping. I'm going to jump ahead now to the 1870s and focus on the Big Island here. And you can see it's got the nice shape, but now we start to get the lava flows that are put on it. And this was made by Charles Nordhoff. Does anyone know the name Charles Nordhoff? I bet you know some of his more famous work. Mutiny on the Bounty. He wrote that book. But he also wrote a book on his trip out to Hawaii as well as Northern California before he wrote Mutiny on the Bounty. And it had this map in it with, you know, Mauna Loa, Mauna Kea, finally got Kilauea on the map. And we've got some of the more recent lava flows. So he's got 1823 down here where the Great Crack is, the Great 1868, 1855, you know, 43, 59, and 1801 here. So one of the first maps that really kind of shows a lot of the lava flows on Hawaii. There's older maps that show lava flows as well. This is just one of my favorites. And then moving on to kind of a smaller inset map to show why looking at these previous maps might be so important. And as you can see here, so this is looking into Kīlaueaʻs. And if you look at Kīlaueaʻs now, it's got a much different shape to it. What's covering the floor of Kīlaueaʻs now? 1959 lava. Well, if we didn't have older maps to tell us and older descriptions from these maps, we wouldn't, well, we might know, but we'd be hard pressed to figure out exactly where and how. You know, 1868 erupted and filled the bottom of this crater. And then 1877 as well, both here and here. And luckily there's an old picture here, bathtub ring, 1868 labeled there, 1877. It's all now covered either by lava here in Kīlaueaʻs, or even this little flow and vent out here are mostly covered by its tephra. And even this, I like the kind of quote from Bingham here about the lava, particularly in here. The names are so confused in the various reports. And that holds true today. I go back and I look at a lot of maps through the past to try and figure out who figured out what and when, and why did they call it this, this, or this. And there's a lot of names that ended up getting confused that you have to sort out. One of the big ones is the 1823 lava flow in the Southwest Rift Zone, which has gone through many iterations and names from, some people call it 1866, some call it the Kamakia Hills, some call it 1823. And that was finally 100 years after it erupted, finally kind of settled by Howard Stearns. So going back to the Big Island in general, you can now see we've got the shape of the island. It looks like it should. And this is a Hawaiian government map from 1886. And this has a lot more detail on it than some of the previous maps. You can see the lava flows here, 1859 coming out, 1881, 1886. But you can also see these stippled patterns that are all over it. That's actually for the Ohia forest. So they mapped out the different forests, they mapped out rangeland. It's just kind of hard to pick out on this map, but it'll be easier as we go. One of the flows I like is this one right here, where you can see it's coming down Mauna Loa, cuts across, and then it cuts all the way across Kilauea as well. Now, technically, if you get a big eruption, this can happen, but back in the day when people were mapping, they didn't have satellite images or aerial images. They had to walk all this region to make a map. And of course, you know, the line you're walking aren't right next to each other every time. Sometimes you're kilometers or 10 kilometers apart. So it's easy to see how you might walk across here, run across an flow and go, okay, I'll map that. And then later come across here and say, oh, that looks like the same flow, even though it might be different, and somehow map it the same. So it all depends on the scale you're trying to map at. Here's a very similar map, but a little easier to read. Again, some of our flows down here have disappeared. In fact, this one's now in the correct position that it should be. And we've got our forests, our rangelands in white here. But it also, we now have, you know, from Waimea Courthouse to different places on the island, or from, you know, through Hamakua to different places on the island. So we're now starting to get the roads in place. We're starting to get the distances and times it's going to take you to travel around the island. Again, a very similar map, but this one's Finney's Hawaiian Directory. So we're now starting to get multi-use maps. Does anyone know what Finney's Hawaiian Directory is? I had to look it up. It's basically your phone book before there were phone books. So it was kind of a list of residents of the island and where they were at, but of course, with no phones or anything like that. I guess if you wanted to send a telegram or, you know, something like that, you would know kind of which post office or where to send it to. But still has our lava flows on it. Got our main geographic features of our Mauna Loa, Mauna Kea, Hualalai, Kilauea, and some of the roads dashed in here. And again, another very similar looking map. A lot of these maps mapped over and over again, but very similar looking. This one's kind of hard to read, but again, you got the stipple pattern with the lava flows. They've gone back now to this lava flow that crosses Kilauea. But this map got a lot of use. There's actually, I found many different versions of this map that have then been overlaid by different surveys. So this is the exact same map, but now you can see it's got these, I guess they're yellow on here. They look green on my computer screen. And these are different public lands that have been mapped out. But you can see we've got the red lines here, the blue lines here, and these are different zones that have been mapped out, and I can't read them, but some of them, I think the in red here are zones considered good for sugar plantations. The blue here are supposed to outline forest reserves. So solid blue are forest reserves, dashed blue are forest resources that are not in reserve, and then we've got the orange here, which are good for rangeland for cattle and whatnot. But yeah, I found a lot of different versions of this map that are just overlaid with, oh, well, we'll draw lines on it and it's good for this, it's good for that. This is the one I like the best. Then we move a little forward in time. We're now up to 1907 with some of our mappings. And I wish I could show every map, but there's just too many. This one is down near Kapapala, Ka'u, Hawaii. And the thing I like about this map is we've now got an outline here for a national park, Kīlauea Volcano National Park, that does not yet exist. The national park did not come into existence till, I believe, 1912? 1916, that's right. So part of me wonders if part of this map was put together by people who were cheering for a national park before it got made to try and lure tourists out. But again, we've got our lava flows here. One of the things I really like about this, you can see these dashed black lines going down. This is the first map I've really been able to find that shows the Southwest Rift Zone. And you can just follow it from the summit down to about the Kamakia Hills here, and it makes its turn down to the 1823 eruption here. And then tourism hits Hawaii. And this is one of the first tourist maps. I'm sure there's earlier tourist maps, but this is one of the first ones from the Hawaiian Promotion Committee that I found in this old newspaper. That the main thing this is for is it does give, you know, places of interest around it. Kilauea up here. It talks about the lava trees and hot springs down here and various other points of interest. And we've even got a zoom up of Kilauea with the trails. And I think this is, it's hard to read on there, it's called the Old Automobile Route on here with Volcano House and places to stay. And then we get one that's just flat out, instead of promotion committee, it's just tourism map of Hawaii. So again, here's the one, lava trees right here, hot springs right here, volcano house up here to stay at. And it does have some of the lava flows on it, some mislabeled. I can see here it says 1823 when this is Kamakia Hills. This one says 1868 when it's actually 1823. So it's tough to say how much attention people paid when putting these maps together, or their goal was just get people on a boat, get them out here to pay to stay at our hotel. And now moving on to some of the more geologically minded maps. So Thomas Jagger, who took over as the second director of the Hawaiian Volcano Observatory, spent a lot of time, of course, up at the summit, watching the lava lakes, looking at the eruptions, and making lots and lots of maps, particularly of Halema'uma'u and what it was doing. So here's a picture from 1917. You can see here, this is the molten lava in the lava lake. There's an island floating around here, a lot of rock sticking up here. And he made very detailed maps at the time. You can see in white kind of the main areas where lava is, and kind of the central pool here, and just the nice flat crater around it. And he's got a little cross section at the bottom. The white again, the molten material with these islands sticking up throughout the lake. And this lake ended up draining in 1919, 1920 during the Mauna Iki eruption. And this is the eruption that was mapped at the time. So this is from Scott Rowland at UH Manoa, but it's based on all the work that Jagger did during the eruption and its different phases. So it was important to Jagger. It's important to us today. You know, we've got an eruption now that's started and stopped several times. We want to know, you know, each time, how much material is coming out of the ground? How high are the fountains? Why is it changing the way it's changing? And that's been happening in volcanology for a long time. So here's an aerial view of Mauna Iki. You can see here kind of this pahoihoi, or lobe that's cutting out. That's this right here. Here's the main shield. You've got your here, your pahoihoi over on this side, and you can kind of see that in this aerial imagery. So just another map, this time of a single eruption and the different phases of it, instead of kind of a larger, broader map that shows us just individual eruptions themselves. And then after this eruption was over, it had drained the lake and Jagger went back out, and this was the map he made. In this case, there's just a little lake at the very bottom. You can't see it in this photo, but you can see the cliffs and the talus here. And then all these lines here are meant to represent talus slopes from this very small lake that's now just filled in with talus instead. So getting a good image of what's going on at the summit and the rift zones through times with individual maps. Moving up into the 20s, this is when Harold Stearns came out. Harold Stearns was a big name in Hawaiian geology. And the thing he's most well known for is groundwater. So he spent a lot of time in Hawaii, not only doing groundwater studies of the Big Island itself, but all the Hawaiian islands. And then during World War II, he went out to a lot of Pacific islands where the military had bases, were building airfields, and ended up doing groundwater studies in Samoa, Fiji, all over the Pacific to kind of aid in the war effort. But you can see here, he was based out of Pahala down here. And this is a very generalized map that he put together. He's got a big book that goes with it in very much detail. But you can see greens here are kind of his older lava flows of Mauna Loa and Kilauea. He didn't differentiate. And then the purples are those younger flows. Again, didn't differentiate. He didn't care what volcano they came from. The darker green here, that's landslide deposits from 1868 that ended up burying the village in Wood Valley. But the thing he was probably most interested in are these lines running across here, which he would have mapped as structures, faults, dikes, and that's what would have been important to him as far as water resources go. So you get a dike, it tends to be impermeable, it impounds water. It's probably a good place to drill to try and find groundwater. And what he really came out to do, and why he was based in Pahala, was helping find water for the sugarcane industry. And then we get into kind of the more modern mapping that we still kind of do today. So this is from George Walker, and I think he put this out in '69. And it starts to have that feel of a US geologic map that we still have. You got your big map sheet here. Here's the Mauna Iki flow. But a lot of these, here's the Kamakia Hills down here. Some of these older flows he didn't know what to do with. Here's the Kauai fault system. And as you can see, he just mapped everything out here. It all looks the same to me. It's a basalt. It's kind of reddish brown. I'll just put it on a map, call it good. But he's got the text that goes along with it. He's got a little cross section here, which you can see is dominated by most of this brownish, tannish unit. And then he's got his explanation over here, which would be youngest at the top, oldest at the bottom, saying, okay, here's Mauna Iki. Oh, I can't read all these. I think this says Kamakia Hills, and on down the line. And he's even got some of these that are not volcanic units at all. So these yellow ones here, he's mapped as landslide deposits from the Helena Poly. There's a lot of sand dunes out here, which I think are some of these yellow ones he's mapped right there. But we've now gotten into the era of kind of the maps as they look like today. Here's Frank Dickmore and Frank Truesdale's map of the East Rift Zone. You see all this in here is kind of that Isla Owl flows, but here's where the East Rift Zone comes out, and you can see a lot of lava flows are kind of concentrated from vents coming out of this region. Again, the kind of reddish colors are the youngest stuff. So I believe this one here is 1840. This is 1790. This is 1960. And then these kind of pinkish red ones over here are 1955. And this on this side is just a continuation of this map. So you can see here's the eastern end of the island right here. And the East Rift Zone actually continues offshore for a very long distance. This is just a bathymetric map. So this is just kind of pointing out that submarine maps do exist. In this case, this is just the topography, but there are people who go out and they get the bathymetry like this, and then they dredge and collect rock samples from the seafloor and try and fill in the gaps. This has not been done on the East Rift Zone. Would be interesting. I know there's people that long ago, 50 years ago now, I think have been out in submersibles, which I think I'd be a little claustrophobic. So I'll leave that to someone else. But again, maps can continue in the submarine realm. And then this one I already showed before. I just wanted to, as the progression goes on in time, this is the Tina Neal and Jack Lockwood map. So the summit, you can see down here, and the more broader area. So here's the 1971 flow, 1974, and then again, this is what underwent collapse in 2018 and kind of makes this map now a little bit obsolete for the summit region. And then this is the map from Dave Sherrod and others that, we've got our reds, our Kīlauea, greens, Mauna Loa. We've got our younger kind of eruptions at the top, and they get older as we go down. And then we also have just a list of units here in case you want to find something specific. And as we get close to the end here, a lot of maps these days have specific patterns and colors that have to go with them. So the USGS has a very thick book. And I mean thick. We're talking a couple hundred pages of patterns and colors that you can use. I will say they're not mandatory to use. So if we go back to Dave Sherrod's map here, this actually runs afoul of a lot of USGS, we'll call them regulations, even though they're more practices, where young eruptions are supposed to be in kind of brighter colors, more reds. But you can see, to make it easier to read, he was allowed to get away with, okay, we're going to make Mauna Loa green, even though that's kind of an intermediate color. We're going to make Kilauea some muted reds, even though there are some older eruptions, particularly in this region, just to make it easier to read. So there's a lot of suggestions in this book that you're advised to take, but it's not necessary. You can get away with saying, I don't like that. It doesn't make sense. It makes the map useless. But, some of these patterns here, and they've got them for every type of rock. So volcanic, sedimentary, igneous, and then you break it down from there. As you can see here, tufaceous rock, crystal tuff, devitrified tuff, volcanic breccia tuff, and it goes on and on and on, as well as any shade, hue of color you can think of, they've got it in there, and they'll tell you what it's best used for, as well as symbols themselves. So, of course, a map without symbols might not tell you a whole lot. But again, we've got contacts, what would be the line between this flow and that flow, which is usually a simple, solid black line. But if you want to know if something's a contact or something's a fault and what type of fault, there's different symbols for that. So, this, I just picked at random, but these are for different types of normal faults. So all these are normal faults. And you can do the same thing with reverse faults, transform faults. There will be a whole page of the different types of symbols you can use for those. And then just as we draw to an end, I kind of pointed out that what we see on the surface can help inform us what's going on underground. So we've got our summit, we've got our southwest rift zone, we've got our east rift zone. But if we take this, I got them out of order, and put it on end, then it kind of gives us a hint of where the magma is. So, we make these maps, we say, oh, well, here's all the vents, and here's where the lava flows are going. That gives us an idea of what's going on. So we've got our Halema'u magma chamber. We know we've got a South Caldera source as well. We know a lot of eruptions occur in the East Rift Zone and the Southwest Rift Zone. This is a little more complicated than just taking a map to do that, but we've got a lot of geophysical, seismic data, geodetic data from GPS and tilt that help inform this as well. But kind of the background data that really pins this down is the geologic mapping. Without the geologic mapping, you're kind of lost. I'll just go back one, and unfortunately Mike Zoller's not here. But again, we continue to do mapping now. I mean, this is the latest version of the map that we have put out. Natalia's shaking her head. Never mind. This is obsolete. Disregard this altogether. But you can see, this was our September 2023 eruption. This was early on in December 23rd of last year. Now last year. But the start of this current eruption. And this is what it looked like on January 2nd. So we're constantly trying to keep the maps up to date on what is going on. There's other types of maps that are put out as well. I wouldn't necessarily call this a geologic map, but you might notice this side of the island. This is from 2018, and it's related to geology because this is during the 2018 eruption. This is a map of where the sulfur is going. So here you can see the highest concentrations of sulfur coming around the south part of the island here and kind of dissipating in these green colors. Matt Patrick, who's also not here, loves to put out his thermal maps. So this is from 2021 and this is from December 2020 through May 2021. And these are different thermal maps that Matt made at the start of the eruption, and these kind of reds and yellows are hotter colors. These blues are cooler colors. And you can see real hot. We've got this island that formed in 2020 and kind of floated around the lava lake. You can see the margins starting to cool. You know, here we had a vent that died out, and this west vent went for a long time before it eventually gets down into this just western lava pond as everything else cools around it. Another type of map, geophysics in this case, from kind of January, February 2023, when we had that dike event that came down and did a lot of cracking. Here you can see the June 2024 Southwest Rift Zone eruption. It's outlined here. Very small eruption, but a very big dike that came down in this direction. And this is a geophysics image. So it's taken from a satellite that kind of measures. It takes an image one day, and then a couple weeks later takes another image, and it can measure the difference in ground movement. And that's what this is showing. So these fringes would all, these different colored bands, fringes, would all represent a certain amount of movement. And as you can see, from red to blue there, each time you go from red to blue, that's 1.5 centimeters of movement. So in total, I forget exactly what it was, but I think this movement represented about 32 centimeters total movement from this event. And this is the same thing here, but now it's got kind of the younger lava flows, Mauna Iki, 1971, 74, as well as these fringes in the background and all the earthquakes that were going along as well. So the eruption would have occurred up here. You can see all the earthquakes coming down along the side of the 1974 eruption, and then a big swath of earthquakes out there at the Kamakia Hills as well. And that's where I'm going to end. And you can take a look here at the difference in the maps between Stearns and McDonald's 1945 map, which just has huge areas that are mapped the same and the young lava flows mapped out, versus the Wolf and Morris map, which is really a template for what Sherrod put together and built on, that kind of picks out the lava flows a little better. And with that, I'll stop talking, and if anyone has any questions. I'm a little